Hi, this is Stephen Barrett from Irvine Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. This is the continuation of the demo for Irvine Chapter 4. This is Part 2. But I added a comment since Part 1 saying those are the variables for Part 1. I'm actually going to use one of these variables for Part 2, but they were created in Part 1. Here in Part 2, I have a new variable. Speed, and I have it as an unsigned 32-bit, and that's going to be the speed of the car. And what I want to do is, well, I want to loop, and I'll get there. There's a method to my madness. So let me do, I want to load into ECX 5 because I want to loop 5 times. Let me add a code label. The loop, I want to include the dumping of the registers, and so loop L1, and I'll add the comment as ECX. This is ECX minus minus. It subtracts 1 from ECX. If ECX is greater than 0, go to L1. Okay. And so what I want to do here is, well, hang on. Let's do this as a starting point. So I want to do a call dump regs before the loop. We should see that EAX is 0. And what I'm going to, oh, no, we're going to see EAX. Let's do it this way. I don't know what I'm doing. Maybe this is a draft. Yeah, that's it. That's the ticket. Let me add to speed 5. Okay. And so I'm going to use this for simulating the accelerate, which I can't spell. And in Java, that would have been speed plus equals 5. Okay. Then for giggles and grins, if I load into speed, we'll see in Chapter 5 for displaying an integer, but for right now, I just want to load it into EAX. So load EAX with speed. Oh, there we go. We'll call dump regs. So if I do that 5 times, my car should be going 25 miles an hour when I'm done. Okay. 5, 10, okay, 15, 20, 25, because the 1, 9, so the 16 to the 1, so 16 plus 9 is 25. Okay. Now, since I was loading up into EAX speed, what was happening here is I actually was adding 5 to what the speed was in memory. Oh, I'm sorry. And let me do one more thing. As we look at, in terms of the runs that we have been doing, the sign flag was 0. The 0 flag was 0. The overflow flag was 0, meaning the adding 5, we didn't overflow. It didn't become 0, and it never went negative. And that'll be because what I want to do next is I want to break. B-R-A-K-E. I want to break. And since the break's going to be similar to the accelerate, let's just copy this. I'll have to make some changes. Let me just copy this block of code. And let's do this as L2, loop L2, L2, But instead of doing an add, I want to subtract, which is like speed minus equals 5. So let's do a break. Break. Okay, and if I only do 5 times, at the end, it should be back to 0. So let's do a, oh, what did I do? Oh, God. I'm thinking of the TV show. Yeah, that's it. That's the ticket. I'm thinking of the TV show. Okay, so the first 5 coming up to here, it's going 25. And then it should be coming back down to, oh, look at that. The 0 flag has been set to 1. So once we subtracted from speed, once we subtracted 5 and speed became 0, the 0 flag was set. So again, later in chapter 6, we'll see how we can do a JZ, not the musician. This is JZ is the actual command, and the letter J, the letter Z, is the command in Java to do a jump when the 0 flag is set. So it'll be JZ and then a code label for where we would go to. But I'm just showing here that at that point, when it became 0, the 0 flag was set. Well, for giggles and grins, let's break 6 times. Because if I break 6 times, I should now be going -5. My story, and I'm sticking to it. So this point right here, this is when the speed was 0. The 0 flag was set, the sign flag wasn't. But then when we go negative, and that's the -5, when we go negative, the 0 flag wasn't set. The sign flag is set because we just went negative. The carry flag was set. And so again, later in chapter 6, we'll see how, we'll see in chapter 6 later about how we can jump based on the flags. I just wanted to show there for that the add and the sub that was there. Wait, let me pause. All right, I just want to stick in one more command. So remember how the arguments one lost was negative, and remember how in part 1, when I loaded it, we saw that there was a negative number in the register because the leftmost bit was 1. Okay, so let's, at the end of this, and first let me just load and move the SX into EVX. The arguments one lost, I just want to see them as is. So this is how, so EVX will have the starting value for arguments one lost for, and so that's going to go into EVX. Let me negate the arguments one lost, okay, and that should make positive. And let's load it into a different register. And so now that I'm doing that, let's do an MOV SX into ECX, the arguments one lost, and see how it is after the negate. So load ECX with updated, and then we'll dump. And so what I want to focus on, I want to focus on this last dump at EBX and ECX. EBX should be negative, ECX should be positive. Let me just, for giggles and grins, let's run this. So the very last dump, there's the EBX, here's the ECX. So remember, if this is 1 is the 16, 16 plus 8 is 24. I had it as 24. Oh, I did have it as 24. Okay, I forgot. I lost that argument. What was the point? Oh, I negated the so up. Um, oh no, that was the. Oh, because I did two things in a row. Anyway, the point was I just wanted to do a negation just so that we can see the negation of a number. So I negated that negative number, and what was there then was positive. Okay, 1037. Let me peek. I'm going to squeeze into this demo. So the author had on one of his slides showing how, like in Java, we would have an expression like this that we would use to calculate the RVAL, and in Java that would be a single statement. This would be the 6 statements that would do the same thing. What I tried to do was in the comments indicate what's going to be in the register at that point. So here EAX is going to have the XVAL, then we negate it, EAX is going to have the negative XVAL. So this piece right here was loaded into the EAX. We loaded EBX with the YVAL, that's this part here. Subtract from EBX the ZVAL, so that EBX has the YVAL minus the ZVAL. That's this part right here. So remember, EAX has this piece, EBX has this piece. So here when we add EBX to EAX, since EAX previously had the XVAL and EBX had the YVAL minus the ZVAL, now we have the result of that, which is the minus 36, and then that gets stored to memory. Here I'm just doing a dump reg so we can see the result of that. And so the very last dump, and you go, oh, wait a minute. So this is 4 bits, and this is 4 bits, so that's 8 bits right there. So taking this DC, let's just try to figure out by hand, let's figure out what the DC is. Okay, so the hex DC. Well, if I take the D, and by the way, this is going to seem funny. Let me do it this way. 1111 I know as being F, right? So 1110 is E, and so 1101, that would be D. So the 1101 would be D, and if that's D, 1100, that would be C. So this is the last 8 bits. Everything above it, oh, I closed it already, sorry. Oh, everything above it is all ones. Those are all ones above it. Okay, so if this is what's there, the DC, well, let's apply the 2's complement. So let's flip the bits, and if I flip the bits, 0, 0, 1, 0, 0, 0, 1, 1, right? Then I add 1. So adding 1 here, by the way, in the classroom I would do this on the whiteboard, and I'm just sticking it here in the code so that you guys can see. And remember, what I'm adding is going to be these. So 1 and 1 is 0, carry the 1, so there's an additional 1 here. 1 and 1 then is 0, carry the 1 to this one. So 1 and 0 is 1, and then the rest are just going to come down. So the 0, 0 and the 0, 0, 1. Okay, so now, and what I want to do is just do the 2's. So 2 to the, so this would be 2 to the 0, 2 to the 1, 2 to the 2, or 2 to the 2, which is 4, 2 to the 3, 2 to the 4, 2 to the 5. So 2 to the 5 is 32. 32 plus 32 plus 4 is 36. So this here was the